Okay, so in this video we're going to simulate the bandpass filter that we designed in the previous video. And this is again something you will have to do, is simulate your filter design. And so if I go here, I'm going to place my parts. Now this is a really simple one, so I just need an analog resistor, a couple of those. And the way I had labeled them, R1 was going to be there, and R2 is here. And then I need a couple capacitors. Make sure that I have analog capacitors, and C1 is here, and then R1 was right here. And then I need a ground. And then I'm going to need an AC voltage source, so I can do a frequency sweep. Then I'll connect everything up here first. So everything's connected. Now let's change these values. This was 820. This was 1 nanofarad. This was 2.2 nanofarads. And this was 47 kilo ohms. And then I'm going to go ahead and label a net here, output, just so I can clearly see the output. And now I have to create a simulation profile. So I'm going to do frequency sweep. And then instead of time domain, we're doing AC sweep, logarithmic, decade, start frequency. Let's go ahead and start at 10 hertz, and at, let's say, cutoff, let's say at least 10 meg. We might go a little bit higher. We'll see how that looks. And 50 points per decade. And then we're now ready to simulate. So I'm just going to go ahead and simulate it. And then I get my graph here. Of course, there's no output on it because I haven't actually plotted anything. Now, as I said, there's a way here. If we go to PSpice, advanced PSpice markers, advanced dB magnitude of voltage. You can only do this after you have simulated the circuit, but that's nice because it gives me exactly what I need as far as my output goes. And we can see, hey, yeah, I get something that looks like a bandpass filter, like we drew. Okay, so let's go ahead and do some measurements on here to see if we got information that is consistent with our computations that we did. So let's go ahead and do evaluate measurements. Now there are several things here. We have a bandpass, the bandwidth. We can do the center frequency, but there's this dB level that you need to do. Now what's weird is you're actually going to go ahead and still do cutoff high pass and cutoff low pass in order to get it, the information that we need. But then also if we scroll down here, we can get the Q factor for the bandpass. So I don't really need to use the center frequency thing anyway, because I can get the bandwidth of the bandpass filter, and then I can get the quality factor of the bandpass filter, and then I can just get it from there. But let's go ahead and just do the bandwidth. Now the which one here? The bandwidth here, the dB level we'll talk about here. So this is saying the bandwidth using minus 3 dB level. Bandwidth, if you want to give it a particular decibel level, that's when you want to do that. And that might be, for instance, if you're wondering what the bandwidth is at -6 dB, or maybe the bandwidth maybe you're getting gain, and so you want the bandwidth at 17 dB or something of that nature. And so what I'm going to do here is bandwidth. I'm going to turn my currents and power off. And we should have one here. There it is. Voltage of the output. That's what we're wanting the bandwidth of. And we can see here, although it's really hard for you to see, let me see if I can go ahead and do the magnifier here. So we can see that we get a bandwidth of approximately 198.54 kilohertz, which is a little bit higher than what we were saying we would get. Then we're going to do similar kinds of things here for the evaluate measurement. And we're going to go ahead and do the cutoff for the high pass. And then I'm going to do another measurement here. And I'm going to do the cutoff for the low pass at the same time here. Now, as we said, this is going to look a little bit unusual for us. I think I did computations wrong in the one video now that I think about it, because I think I said 200 minus 1.5 is 285, which is clearly not. Well, you'll catch the error. It's arithmetic. You guys are all smart enough, you should catch my arithmetic error. I'll also put a note of it in Blackboard. So if I look here at these, we can see that, yes, I have a cutoff frequency. Now, you might say, wait, it's a high pass, but remember, that's what we are looking at here. I have a cutoff frequency of 1.5, a cutoff of 200, which is exactly what I was designing for. So this looks like it's going to be a very good design. And then if I want to, for instance, do the center frequency, we have to give it the output and then a dB level. So I'm going to say, I think I can do a negative there, and I'm going to say -3. Oh, one thing I forgot to do here is we have to make sure that the voltage has been converted to dB. Maybe that's not the issue here. Let's do this. Let's try this again. Maybe it's just +3 that we put in there. Bandwidth, output 3. Yeah. So you don't put the negative in. So let's go and do this again here for like the center frequency. So the output, comma, 3, oh, the comma's already there. And it says the center frequency is 100 kilohertz, which is not at all what our center is. It must not be using the same formula, so we're going to have to see that for a second. There's something wrong going on with its center frequency computation. But we can still evaluate these measurements. If we do the Q, we can get the Q factor as well. Which based off the center frequency that it's computing and the Q factor. Now, that center frequency there, that 3 might not be correct as far as the dB levels go. So I'm not very familiar with using, let's magnify again. I'm not very familiar with using the center frequency or this Q here, so I typically measure my cutoff frequencies, the bandwidth, and then simply use the equations that we have to compute the Q and the center frequency to compare them to our measured results. And I must have zoomed in on this, so, whoops. I must have clicked in and zoomed on that by accident, so zoom fit. So we have our bandpass filter there. Now, I had mentioned that there are loading effects here that are going on. So I'm going to make this 470 ohms, which if I make that 470 ohms, I'm making that 100 times smaller. So if I make that 100 times smaller, I need to make this 100 times bigger. So that would be 220 nanofarads. So in theory, we should get the same output graph. And it still looks like a bandpass filter, but look what you have here now. It doesn't go up to 0 dB. It's going down at minus 10 dB. And let's go ahead and toggle my measurements here and see what happens when I do the cutoff frequencies here. And the cutoff frequencies are completely wrong as well. It's saying that the cutoff frequency, here let me show you here. It's saying that the bandwidth is 532 kilohertz, cutoff 560 and 533, which is not at all what we designed for and not at all what it's supposed to. Because what it's doing is it's doing minus 3 dB from this maximum value. But this is not getting up to the 0 decibel level that we want to. And what's happening, again, is that there's this loading effect that's going on. And the reason is this loading effect is that, imagine equivalent resistance here. We wind up, without going through all of the formulas here, you wind up with R1 in parallel with R2 as far as a loading effect for first stage. So if R1 is in parallel with R2, this would be equal to, well, let's just do a quick computation here. If we had 470 ohm times 480 ohm divided by 470 plus 820, instead of having that 820 ohm resistor like we are saying we need there, we really are winding up with a 175 ohm resistor because of the loading effects. But now if I go, which is what's causing all of our gains to be reduced. And it's the same thing for the second stage as well, the high frequency stage. Now if I instead though have 820 and I do this and it's in parallel with 42 kilo ohms. So just a second here. Let me reset this here. So let's do 42,000 inverse plus 820 inverse. We still essentially wind up with 820 ohms. Yes, it's reduced down to 805 or 804, I mean, but it's still essentially 820 ohm. And so the loading effect is significantly reduced. And that's because of the fact that we've made this, in the original one here, that we made this 47 kilo ohms. So you absolutely have to have that there in order for us to not get that loading effect. And so if I resimulate this again, putting them back to the way they are, we can see now the graph goes up to 0 decibels. So we are getting the fact that we don't have that loading effect in place. Now, the next set of labs we'll move on to after this to kind of finish up the semester are going to be active loads as far as active filters. And there's two advantages with active filters. One is we don't have the same loading effect that we have going on here. That's a huge advantage, that we don't have a loading effect. And number two is that we can actually get gain out of these things. So we can both filter and amplify at the same time. Now, typically the way they're designed is that you filter and then you have a separate stage that amplifies. You typically don't try and do amplification and filtering at the same time. All right, but that's how you can go ahead and do these simulations here. So I'm going to go ahead and pause and stop this.